Good day, everyone. Today's topic is rational function. So, what exactly is rational function? A rational function is defined as the ratio of two real polynomials with the condition that the polynomial in the denominator is not a zero polynomial. Rational function is denoted by f of x equals to p of x over q of x, wherein p of x and q of x are polynomial and q of x must not be equal to 0. Why must q of x not be equal to 0? Because if you have 0 as your denominator, it will be undefined. Here are some examples. Example number 1. X plus 1 over 0 is not a rational function because the numerator is a polynomial but the denominator is 0. We cannot divide by 0, therefore it is undefined, so it does not apply to the condition of a rational function. Example number 2. X to the power of 1/2 plus 3 over x squared is not a rational function because the numerator has a fractional exponent, therefore cannot be solved. Example number 3. X squared plus 4 over x plus 3 is a rational function. Example number 4. X plus 1 over x plus 3 is also a rational function. And lastly, example number 5. X squared plus 3x plus 2 over 0 is not a rational function because the denominator is 0. Here are some examples or problems involving rational functions. First example is, average speed can be computed by the formula S equals d over t. Consider a 100-meter track used for foot races. The speed of a runner can be computed by taking the timer for him to the track and applying it to the formula S equals 100 over t, since the distance is fixed at 100 meters. Solution: let x represent the time it takes to run 100 meters. S of x equals 100 over x. Let x be the runtime and the speed of a runner in the meters per second, where S of x equals 100 over x. Construct a table of values for the speed of a runner against different runtime in the table of values. We have gotten the runner runtime from 10 seconds to 20 seconds. All we have to do is substitute the value to the formula, so if the x is 10, the average speed of the runner is also 10 meters per second, and so on. We can refer to the table of the example. In order to graph this, we have to plot the points on the table of values. So, A, 10 and 10, B, 12 and 8.33, C, 14 and 7.14, D, 16 and 6.25, E, 18 and 5.56, and F, 20 and 5. And the graph would look something like this. Second example, C of t equals 5t over t squared plus 1 in milligram per millimeter represents the concentration of a drug in a patient's bloodstream t hours after the drug was administered. Construct the table of values for C of t for t equals 1, 2, 5, and 10. Construct a table of values for the hours after the drug is administered. Here in the second example, the value for the time are already given, so all we need to do is substitute the given value to the formula. Same with the first example, we'll need to plot the points in the table of values. A, 0 and 0, B, 1 and 2.5, C, 2 and 2, D, 5 and 0.962, and E, 10 and 0.495, and the graph will look something like this after plotting the points. Third problem is a real-life example involving rational function. The local barangay received a budget of 100,000 pesos to provide medical checkups for children in the barangay. The amount is to be allotted equally among all the children in the barangay. Write an equation representative of the allotted amount per child, which is the y variable, versus the total number of children, which is the x variable. Thus, the equation will be y equals 100,000 over x. Here, we assume if the barangay has 10 children, each child will receive 10,000. If there are 20 children, each child will receive 5,000. And if there are 50 children, each child will receive 2,000. And if the barangay has 100 children, each child will receive 1,000, and so on. Fourth example, The local barangay received a budget of 100,000 pesos to provide medical checkups for children in the barangay. The amount is to be allotted equally among all the children in the barangay. A philanthropist wants to supplement the budget allotted for each child by providing an additional 750 pesos for each child in the barangay. In our fourth example, we added that a philanthropist wants to provide an additional 750 pesos for each child of the barangay. If g of x represents the new amount for each child, construct a function representing this relationship. Thus, the equation will be g of x equals 100,000 over x plus 750. So, if the barangay has 10 children, each child will receive 10,750. If there are 20 children, each child will receive 5,750. If there are 50 children, each child will receive 2,750. If there are 100 children, each child will receive 1,750, and so on. Fifth example. Suppose a family spends 15,000 pesos monthly for food. On the average, an amount of f of x of money each member, which is the x. Write an equation which shows the relationship between f of x and x. X equals number of family members, and f of x equals amount of money spent for food of each family member. Thus, the equation will be f of x equals 15,000 over x. So, if there is only one family member, the amount money spent on food is 15,000 pesos, and there are two, the money spent for food, each of them is 7,500 monthly, and if there are three members of the family, the money spent for each of them is 5,000, and so on, which we can refer in the table presented. Next, we're going to talk about graphing rational functions. But first, let us recall some of these terms. Domain, set of all real numbers except the zeros of the denominator. The domain of a function is a set of all values that the variable x can take. X-intercept, let y equal 0. X-intercept is the x-coordinate of the point where graph crosses the x-axis. Y-intercept, let x equals to 0, is the y-coordinate of the point where the graph crosses the y-axis. Vertical asymptotes, restricted value or values for x, and horizontal asymptotes, conditions, d, degree, and numerator, and another d for denominator. D and n less than d on d is y equals 0. D and n equals d and d is y equals ab or leading coefficient. D and n greater than d and d is none. Zeros, same as our x-intercept. The zeros of a function are the value of x which makes the function 0. Whole or removal or discontinuities are the values or inputs that causes a numerator and denominator to be 0. Our first example, fx equals x squared minus x minus 6 over x minus 3, where the domain x minus 3 equals 0 is x equals 3. So our domain is x such that x is an element of real numbers except 3. X-intercept, y equals x squared minus x minus 6 over x minus 3. 0 equals x squared minus x minus 6 over x minus 3, which we're going to cross multiply 0 and x minus 3. So 0 equals x squared minus x minus 6, which we're going to factor this out, is 0 equals x minus 3 x plus 2. X minus 3 equals 0 is x equals 3, and x plus 2 equals 0 is x equals negative 2. Since the domain tells us that x is not equal to 3, so we're only going to consider negative 2 and 0. Therefore, our x-intercept is negative 2 and 0. Y-intercept, y equals 0 squared minus 0 minus 6 over 0 minus 3. Y equals negative 6 over negative 3 is y equals 2. Therefore, the y-intercept is 0, 2. Zeros is x equals negative 2. Vertical asymptotes none. Horizontal asymptotes is also none. And lastly, whole. Fx equals x squared minus x minus 6 over x minus 3. X minus 3, x plus 2 over x minus 3, which has the common factor x minus 3. Thus, we're going to cancel that common factor. X minus 3 equals 0. x equals 3 is the abscissa or the x to get the y. X plus 2 equals 3 plus 2. We're going to get the remaining numerator, x plus 2, then substitute the value of x, which is 3, so it becomes 3 plus 2 equals 5. So 3, 5 is our whole. Second example, which is f of x equals 1 over x minus 1. Domain, x minus 1 equals 0, x equals 1. So our domain x such that x is an element of real numbers except 2. X-intercept, y equals 1 over x minus 1, 0 equals 1 over x minus 1, which we're going to cross multiply, will result 0 equals 1. Therefore, there is no x-intercept. Y-intercept, y equals 1 over x minus 1, 0 equals 1 over 0 minus 1 equals 1 over negative 1. Y equals negative 1. So, 0 and negative 1. Zeros is none. Vertical asymptote x equals 1. Horizontal asymptote y equals 0. And lastly, whole is none. Third example. In this example, we will make an interval table or sign table, and we will now graph our equation. But there's no need to worry, for this is as easy as eating. So, our third example is f of x equals 5x over 2x minus 8. The domain, 2x minus 8 equals 0, 2x equals 8, x equals 4. So our domain is all real numbers except 4. Zeros, 5x equals 0, x equals 0. And x-intercept, 0 equals 5x over 2x minus 8, 0 equals 5x, x equals 0. We're going to take note that in this part, we're going to cross multiply 0 times 2x minus 8, that is 0 equals to 5x, divide both sides by 5, so x is equal to 0. Y-intercept, y equals 5 times 0 over 2 times 0 minus 8. 0 equals 0 over negative 8 is y equals 0. Therefore, there is no y-intercept. The vertical asymptote is x equals 4, and horizontal asymptote is y equals 5 over 2. Fourth example. F of x equals x minus 2 over x plus 2. Domain, x plus 2 equals 0 is x equals negative 2. So our domain is all real numbers except negative 2. Zeros, x minus 2 is x equals 2. X-intercept, 0 equals x minus 2 over x plus 2. 0 equals x minus 2 is x equals 2. Y-intercept, y equals negative 1. The coefficient of your constant, and that is negative 2 over positive 2. Negative 2 divided by positive 2 is equals to negative 1, hence our y-intercept. Vertical asymptote, x equals negative 2, and horizontal asymptote, y equals 1 over 1 equals 1. The leading coefficient of numerator and denominator, that is y equals 1 over 1 equals 1. This graph shows our vertical and horizontal asymptote. This is the first thing you will do. Next, plot the intercepts, so we have 2 for our x-intercept and negative 1 for our y-intercept. Then, we make our interval table. So in order to make one, you only need the values from your vertical asymptote and 0, and that is negative 2 and 2. So our test point in x less than negative 2 is negative 3, x is greater than negative 2 but less than 2 is 0, and in the x is greater than 2 is 3. Since we already picked the values for our test points, all we need to do is substitute the values to x. So here, negative 3 plus 2 is negative. Negative 3 minus 2, the answer is negative 5, hence the negative sign, and so on. Lastly, the signs on the last column indicate our graph. It tells us if the graph is above or below the x-axis. And now, this is what the graph looks like. Fifth and our last example is f of x equals 3x squared minus 8x minus 3 over 2x squared plus 7x minus 4. So here in our last example, the given is trinomial, so we need to factor it out. F of x equals 3x plus 1, x minus 3, over 2x minus 1, x plus 4. The domain 2x minus 1 equals 0, 2x equals 1 is x equals 1 half, and x plus 4 is x equals negative 4. So our domain is all real number except 1 half and negative 4. Zeros, 3x plus 1 equals 0, 3x equals negative 1 is x equals 1/3. X minus 3 is x equals 3. X-intercept, 3x plus 1 equals 0, 3x equals negative 1, x equals negative 1/3. X minus 3 is x equals positive 3. And y-intercept, 3/4 or the coefficient of your constant. And then vertical asymptote, x equals 1 half and x equals negative 4. And the horizontal asymptote, y equals 3 over 2. Then we make our interval sign table since we have 2 values for vertical asymptote and 2 values for 0. We'll have 5 intervals. Take note that we have lowest value should always come first. So we have here on our left side negative 4 and then followed by x is greater than negative 4 but less than negative 1/3, and so on up to the highest value, which is 3. Pick a value that fits the statement. Again, you can pick any number as long as it fits the statement. So in our case, we pick negative 10 and x is less than negative 4. We pick negative 2 and x is greater than negative 4 but less than negative 1/3, and so on, which we can refer to the table presented. Now, we distribute the values. And x is less than negative 4 is above x-axis in x is greater than negative 4 but less than negative 1/3 is below x-axis. Again, we can refer in the table presented. So, when you graph, it will look something like this. So, again, we graph first our asymptotes. And then we could go ahead and plot the final graph. And it will look something like this. So that is all. Thank you so much for listening, and I hope you have learned everything about rational functions. I'll see you all again next time. Bye!